this recording because I accidentally showed some screen that I think should not be shown on screen. There's some like private information, so I trimmed the previous section. I think it's still the same problem. I think I'll start back up from theorem 3.2.10.2. So the idea is to basically show that you can make some h which is minus g, and then show that h has limit of the limit which is the negative of the limit of g, and then it becomes the same as problem 1. So we want to show this small lemma. I think for me at least that's one way to approach it. If you want to work with epsilon deltas for minus, I'm not sure how you would really go about that. I think that'd be a bit more annoying in my head to try and deal with. For this part 5, I think I need to work on it. I haven't finished it really. I started with this lemma that the limit of 1 over g is equal to 1 over the limit of g, for example, if the limit is not 0, of course. So let's first show this lemma and then proceed with the rest. So actually I think this might be a bit trickier than I thought it would, because you must show that, for example, 1 over gx minus 1 over L is within a certain limit, but then that is within epsilon. But I don't think that's so easy to show. So let me write some quick scratch notes regarding that. Yeah, so I think you somehow can bring it back to L minus gx, but you then have to deal with the denominator. L is a known value, so we can consider it to be a constant. So let's quickly do that. Yeah, this jamming sometimes happens with LaTeX or LaTeX. It sort of like stops compiling, even though it really has no good reason not to. Undefined control sequence. Yeah, I think sometimes in situations like this, you have to probably quit the program. Yeah, it's not great. It's not great when you have to do this, honestly. I think it was this one. Was it? No, that's the previous block one I had. Is it this? Yes. Okay, so this one. Okay, so let me just compile again, or remove the textbook here. Okay, so one thing we need to be careful about is how to make sure that the g of x can be bounded. I think there was something in the section earlier about g of x being bounded when it's within a certain area of the limit let's say, within some certain delta neighborhood of the limit. But the signs always annoy me, so I need to just think about it. So let's say if L minus G of X is lesser than some other value. Let's say if it was lesser than, say, epsilon over L times some other value M, somehow that would make it less than this epsilon over LGX, then what M would we need to make this true? So we would need, I think, a bigger M, because if M was greater than G, absolute value of Gx, then this value would be lesser than or equal to this value, because with a larger denominator you get a smaller value. So effectively we want M is greater than or equal to G of X absolute value, which is perfect because we do have something that says that. So I think that's the exact situation we want to be in. But to make this possible, we need to first find the bound for G of X. So that is something that we noted earlier from one of the previous parts of this section. Let's say, was it here? Yeah, I think it was here. Was this a lemma? Yeah, it was a lemma, so we can use it directly. Let's know that lemma said applies that. Okay, maybe after we choose the epsilon neighborhood or delta neighborhood, we can't use it. Or no, I think we must use it first. Okay, so I think this is a little bit confusing. We need to find neighborhood first, find the M, and then find the minimum between that neighborhood and the neighborhood based on the epsilon chosen from G of X and so on and so forth, and something like that. Yeah, I think that will be how it works or something. Or no. Jeez, okay. So we can make this fancier and use the fraction symbol. There's nothing too crazy here. And so here I think it's good to use some quick align because we need multiple expressions at least to explain this out in a more precise manner. So first we can apply the fact that it's less than delta prime. Oh, I think I need an absolute value here. Yeah. So now we can plug in this value, and then it can expand out. Oh, I think, darn it, did I do something stupid? Did I need this mapping for sigma? Yeah, I think I didn't need it. Oh gosh darn it, what? Yeah, I think you can only say g of x minus L is less than delta because, or gx minus L is less than epsilon because you use the x which is chosen, you use the delta which is chosen for this g from this fact that the limit of g is equal to L. So if you use the delta for the epsilon with the normal g, then you can show that the value is less than epsilon minus, oh sorry, the value for epsilon. Wait, what am I even saying? No, I think I did something stupid. I need to not do something stupid. Yeah, I think I need to do this. Oh, no, not that. Like this. Yeah, I think this would work a lot better, perhaps. Wait, how do you do this again? Left. Yeah, I think now it makes sense because you specifically chosen delta so that if x is in the delta neighborhood of c, then g of x minus L is less than this value, epsilon over Lm, where L and M are known values, where else the limit at M is the bound that you discovered for some arbitrary open neighborhood. Yeah, now it makes sense. So here I think you can say that, let's say x is in this neighborhood of C. Okay, I guess that was a bit, oh, didn't have a closing bracket, that's why. Yeah. So let me just clean out the scratch work. So since the lemma is demonstrated, we can move on to the main proof. Let's say make this the main proof. Maybe the main proof can be in the next page. Let me see the question again. Oh, that's too big. Yeah, this is quite a lot to type out. It's a bit annoying. Maybe I can just quickly define it first. Yeah, somehow don't think this was the best way to write the proof, but I mean, it gets the job done, so I'm not going to complain excessively about it. Okay, so here, this is a direct application of the subtraction one, I think. If you, assume that f plus g does have a limit, and you subtract f, then g should have a limit. But of course, this is assuming there's only two possible states, that the limit either exists or it doesn't, and there's no third state where. But I mean, maybe that's a bit absurd, because the definition of does not exist means that there doesn't exist any real number such that the definition of limit can be satisfied. So the opposite of that naturally would be the case, that there is some number where the definition limit can be satisfied. So these two are opposites in a way. And, or I mean by opposites, I mean the union of those two possible outcomes cover all of the possible outcomes. Perhaps that's said in a very inelegant way. Yeah, similar situation was this. You want to use the division one. Use this to divide this, and get that g should exist, but it doesn't actually. And then, yeah, you get into trouble for that. But I'm too lazy to write that out. I think I should move on to some physics, maybe some physics reading. I was looking at this book, Taylor's Mechanics, Classical Mechanics. Go to that quickly.